Alright, so I think we're live now. Yeah, we're live. Sorry, chat. I think. Yeah, first I thought we were. I thought I was live already. Sorry, that's my bad. So yeah, we're gonna go over a physics. Gonna go over a physics past paper. So it's, well, I guess it's not quite a past paper, but it's a specimen paper. So So, well, I guess we have a choice for like what we do today, but I could, first of all, I could go over the paper one, or I could go over paper two, or I could go over A4 and A5 because I think those are the toughest units. So that's like rigid body motion, rotational mechanics, and special relativity. So paper one is all multiple choice. Uh, Paper two is long answer. So, what do you say, chat? What's the plan? Yeah, what do you guys say, chat? Paper two? Yeah, I was thinking paper two as well because it's long answer. Usually the harder questions are in paper two. I'll pull up the physics IB data booklet. All right, let's get started. So we'll go over paper two then. This is see. That's paper two. There you go. Okay, let's make this a bit bigger. Okay. So paper two is 2 hour 30-minute exam, but we should be able to finish a lot faster since we haven't covered all the topics yet. So there will be some questions I'm just gonna skip over. Ooh, relativity. Good. Okay. I want to go over that. Okay, we'll start with question one. And chat, feel free to like work along with us. Feel free to do the questions with us. Okay. So first question, a block of mass 45 kilograms is placed on a horizontal table. There is no friction between the block and the table. An object of mass 15 kilograms is placed on top of the block. A force F acts on the block so that it accelerates. The acceleration of the object and the acceleration of the block are the same so that they do not move relative to each other. The coefficient of static friction between the block and the object is 0.6. State the nature and direction of the force that accelerates the 15-kilogram object. So this is an IB specimen paper. Okay, state the nature and the direction of the force that accelerates the 15 kilogram object. So the 15 kilogram object is obviously accelerating with the 45 kilogram object. So it's obviously direction is to the right. And there's only one contact that could possibly be providing this force, and therefore it must be the static friction force. Determine the largest magnitude of F for which the block and the object do not move relative to each other. Okay, so just to make sure we don't confuse anything, we'll draw the free body diagrams. So this is of, which one is the object? The block. So this one is the block and the top one is the object. So for the object, there's only two forces, or there's only one really, which is friction, right? Now for the block, there are two forces. Now friction is obviously going to oppose the other directions because, you know, Newton's third law, there must be an equal and opposite reaction. So friction obviously goes this way along with the force that's applied. And I don't think there is any friction between the surface. There's no friction between the block and the table. Okay. So now we can work out, and we can calculate the coefficient of static friction actually. So Ff is equal to Fn times the coefficient of friction. Fn is just the mass of the block, the object. Well, I guess there's a normal force and a supporting normal weight and normal force, but I just won't write that. So mg mu. Does it give the mass? So 15 kilograms. Okay, so we'll say m1 for now. So the friction force we can calculate that way. For which the block and the object do not move relative to one another. Okay, so if the objects are not moving relative to one another, is G 10? Yeah, G is, let me check the data booklet. Let's see what it says. Okay, so they want you to use 9.81 for G. So they want you to use G equals 9.81. Yep. So, since the friction force, well, this is the maximum friction force. The friction force is this. Therefore, the acceleration must be Ff over m1, which is g times mu. Right? The acceleration of the object, I should write max actually. The maximum acceleration this object can have is the friction force divided by m1 by Newton's second law, and that's g times mu. So therefore, since we have a max, we can write another equation using this, which is F minus Ff over m2, so that's the mass of the big block, equals a max, because we want the maximum force, and that's going to be g times mu. So now we can substitute stuff in. So we know F minus m1 g mu over m2 equals g times mu. Therefore, F minus M1 g mu equals M2 g mu. Therefore, F equals M1 plus M2 g mu. And then you can substitute your values. I won't do the calculations, but yeah, just to save time, we'll move on to the next one. Question 2. And yeah, any questions, chat, feel free to just ask. I got the chat open right on my monitor, so I can respond pretty quickly. But yeah, know that there is a delay, so by the time you receive, by the time I see it, it's probably gonna be like at 30 or 40 seconds after. Okay. A spacecraft is flying past a space station at a relative speed of 0.8 c. Beacons R and F at each end of the spaceship emit light pulses at the same time according to the observers on the space station. The pulses are emitted 1,200 meters apart as measured by the space station observers. So, okay, calculate the gamma. This is the easy part. So literally just plug it into your equation. That's 1 over the square root of 1 minus v over c squared, which is 1 over square root of 1 minus 0.8 squared. Should be 1 over 0.6, which is 5 over 3. Calculate for the reference frame of the spacecraft the distance between the light pulses. So, the distance between the light pulses. So, emit light pulses at the same time. Oh, okay. So it's okay. That makes sense. Right. So, for part B, the distance between the light pulses will just be the distance from R to F. And we know that the length contracts, so therefore L is L0, the proper length, over the gamma factor. And since the proper length is 1200 over 5 over 3, that should give 720 meters? And chat, check my calculations, because I'm not... I guess I should have a calculator on me. Hold on. Yeah, I'll have my calculator on me. Yeah. Yeah, 720. Good. Okay. And chat, if you want me to review relativity, I could do that. So we can derive all the Lorentz transformations from start to finish. Yeah. Okay. The time between the light pulses. So the time between the light pulses will just be... Now, where is the spacecraft? Okay. So the time between the light pulses. So the first one... So pretty much this is the diagram. That's 720 meters. The time between the light pulses... So the first one, obviously... Let's say the spaceship is right here, right? The first one is instantaneous. The second one would need to travel that 720 meters. So t is d over speed of light. So that's 720 divided by 3 times 10 to the 8. Should be 2.4 times 10 to the negative 6 seconds. Right. Determine which light pulse happened first. Do they want a space-time diagram for this, or? Okay. So I guess one way to do C would be to draw a space-time. The other way, you can just use Lorentz transformations. So obviously, when you're moving with speeds, well, I'll do Lorentz first. So using Lorentz transformations, determine which light pulse happened first. Are they saying when it's emitted, or it should be when it emitted, right? Yeah, it should be when it's emitted. So using Lorentz transformation, this is a time transformation. So t this is t prime. T prime equals gamma x t plus because in the spacecraft's frame, the space station are traveling to the left, and therefore v is negative. So therefore, whatever's here is plus x v over c squared. X prime v over c squared, right? I'm just gonna check that. Describing fields, relativity, t prime. Wait, is it t? T prime. Wait, t prime is the negative one? Gamma t minus. Oh, okay. Sorry, chat. Yeah, right. So if you use this equation, obviously x is positive, v is positive, so therefore, well, we guess we wouldn't know unless we plug it in, right? So what we can do here is we can set the time that it receives r to be 0, and the distance at r to be 0 as well. So then therefore, in the spacecraft's frame, the second emitted light would have occurred at gamma t should be 0, because in the observer's frame it's 0, minus the distance in the observer's frame, 1200 times 0.8 c over c squared. And this should be a negative value, right? So therefore this t prime, so t prime is when it receives the light from F. Any reason we're using the old data booklet? Is this the old data booklet? This one is the new one? Is this a new one? This one should be. But anyways, as I was saying, t prime is obviously negative, therefore the beam of light at F happened first. You can also do this with a space-time diagram, so I'll just draw that real quick. So, well, I guess it would be kind of hard, right? Because realistically, you need to do a transformation as well. But yeah, let's just say this is 0.8 c. You have one thing occurring here, the other one is at 1200. When would it receive it? Well, this thing would receive it instantly here, but the time axis, or this is the time axis. So the time axis would really be like this. All right. Right, next one is question 3. In a microwave oven, electromagnetic waves are emitted so that standing waves pattern is established inside the oven. A piece of chocolate is placed inside the oven and the microwaves are switched on. The chocolate is stationary. Melted points form on the chocolate. The diagram shows the pattern of the melting on the chocolate. Each square has a length of 1 centimeter. So, outline how the standing wave pattern of the melted points is formed. Standing waves, just when it bounces back. Determine, taking appropriate measurements from the diagram, the frequency of the EM waves in the oven. So if each of these are 1 centimeters, the distance between them, 1, 2, 3, 4, 5, 6 point, I'll say like 6.1. So the distance between them is 6.1 centimeters. And we know that that is half of lambda. So lambda over 2 is 6.1 centimeters. So lambda is 0.121 meters. And then they want us to find the frequency. Now frequency is just c over lambda, so you can find that pretty easily. All right, question 4. Satellite moves around Earth in a circular orbit. Draw an arrow on the diagram to represent the direction of the acceleration of the satellite. This one's pretty simple. So obviously, satellite, let's say, is moving like that. Acceleration arrow always points towards the center because it's uniform circular motion. The following data are given. Mass of Earth, m equals 5.97. Okay. Kepler's third law of orbital motion states that t squared equals kr cubed, where k is a constant and r is the orbital radius of the satellite. Do we learn Kepler's laws in IB? I don't think we do, actually. So it wants us to show that k equals 4 pi squared over gm. Yeah, I don't think we learned Kepler's, right? Right, but they... Hello. Show that k equals 4 pi squared over gm. Okay. So k, we obviously... First of all, we need to represent k using t cubed over r squared. So then we want a relationship between t and r. So realistically, the satellite shouldn't really matter. But let's just say... Okay, let's just say that the satellite is orbiting at a radius r. So radius equals r. So r we already know. right? We'll represent everything using r, so that makes sense. Therefore, we can calculate the force that this, or the acceleration that this satellite will receive, right? So acceleration, so F is equal to gme, m of the satellite over r squared. So therefore acceleration is, you divide that by the mass, so gme over r squared. Then using that, we can find that, or I guess we can just write force, that's fine. So the force of the acceleration has to be the force, has to be the centripetal force, which is also equal to m w squared r. So I use w here instead of v because I want something to do with the period, and I'm only going to get information about the period when I use the angular moment, the angular speed. So therefore m's cancel out, and I can represent w squared using 2 pi over t squared r. Therefore we have a relationship. Oh, sorry, t squared, and this is r cubed. That's my bad. T squared over r cubed, right? So we have a relationship. So therefore gme over r squared equals 4 pi squared t squared r. Just shuffle some stuff around. gme over r squared equals, oh, not over r squared, equal over 4 pi squared equals r cubed over t squared, which we have from up there is just k. Right, so this is just building a relationship between centripetal force and force of gravity. Determine the height of the satellite above the Earth's surface. So they told us the period t of the satellite. Therefore, using the period, and we know these are all constants, right? So we can represent t using t squared is just 4 pi squared r cubed over gme. Right, so 4 pi squared r cubed over gme. They told, or no, we're finding radius, right? The height. Oh shoot, sorry. So we want to represent it the other way. Right, so therefore r cubed would be gme t squared over 4 pi squared. Therefore we can find r pretty easily from here. And then obviously the height would just be the r minus the radius of the Earth. Oh no, that's not C. My bad. That is part 2. So part C says, the atmosphere exerts a small viscous drag force on the satellite. Outline how the total energy, kinetic energy, and the gravitational potential energy change for the satellite during one orbit. So obviously, okay, this is actually pretty interesting, because what happens is that the speed actually increases as the height decreases. So we know that the total energy, which I'll represent here, is going to decrease, right? So this is ET. Or I'll just write E. So that's E. It's going to increase. So that's energy, and that's time. So obviously E is going to decrease. And potential energy? Well, potential energy is going to decrease as well. But what's actually funny is that kinetic energy actually increases with a decreasing E. Because as you actually get closer to the Earth's surface, you move faster because of your period is shorter, right? So the kinetic energy actually increases. So kinetic actually goes like this. So that's K. And potential would decrease, so something like this. So that's P. Okay, part 5, this is about flux, so I'll skip that one. Smoke detector. Nuclear decay. Okay, so we haven't learned about nuclear decay either, so I'll skip this one as well. Okay, a star delta val A is a main sequence star that has a black body spectrum as shown. So this is question 7. Show that the surface temperature of val A is about 9,000 Kelvin. So we can use Wien's law. Is that what it's called? Wien's law? Let's see if I have it here. We want... Let's see. Oh, I think we missed it. It's heat. Right, Wien's law. So lambda max times T equals 2.9 times 10 to the negative 3 millikelvins? Is that millikelvins or math? Wait. That's just millikelvins, right? Oh no, that's meters Kelvin. Okay, meters Kelvin. What? That's the most confusing way to represent that. Okay, meters Kelvin, right. So lambda, okay, what's the question asking for? Surface temperature? Okay, lambda max, we can see it's about 0.31. I'll see 0.31. So 0.31, and that is in meters. So 0.31 times 10 to the negative 6 meters times T equals 2.9 times 10 to the negative 3. So therefore we can get T is approximately 9,000 Kelvin. Apparent brightness is this, and it's this from Earth. So estimate the radius. So the apparent brightness, apparent is always, it always means from as an observer, like what we see, right? So the apparent brightness of what we see is 2.2 times 10 to the negative 9. Apparent brightness, say brightness is just intensity, so I equals 2.2 times 10 to the negative 9 watts meters squared. Okay, and it is 6.2 times 10 to the negative 10 to the 14 kilometers from Earth. So basically, distance is 6.2 times 10 to the 17 meters. So apparent brightness. Okay, so using this, we can estimate the intensity of the star itself. So obviously we need to use the Stefan-Boltzmann law, which is where is it? The sigma law. Okay. Total power output. Right. So we have L equals sigma A to the 4. And did they give us an emissivity? Has a black body. Okay, so we're assuming that it's a black body. Right. So we can get the luminosity. Now, the brightness at the surface, so let's say this was the star, Bel A, then the brightness at the surface, we would have to take luminosity, so the brightness at the surface will be luminosity divided by the surface area. So brightness, we can represent this as L over 4 pi r squared, which is sigma A t to the 4 pi r squared. Therefore, the brightness would obviously hold on a second. Okay, yeah, so we can represent this brightness. Obviously, it needs to equal the intensity that we are seeing. And that is just going to be the brightness that we see is 2.2 times 10 to the negative 9 watts per meter squared times the surface area that we see, which is massive, obviously. So let's say this is the Earth. And that's going to be D. So obviously we see something that's much larger. So the total intensity, we need to multiply this by the total area that it's covering, which is going to be 4 pi d squared, right? And we equate this with sigma A t to the 4 over 4 pi r squared, and then you can solve for r. All right, question C, radius of the sun. Sketch on the Hertzsprung-Russell diagram the position of... Okay, never heard of this diagram before, but let's see what we can make out of it. So luminosity, as radius goes up, and temperature. Oh, so it wants us to represent. So the radius of the sun is 7 times 10 to the 5. So after we find the radius, we can represent the radius of vel A using the radius of the sun. Right? We can represent that as how many Earth-Sun radiuses, and then we can determine where it is. We know the luminosity, we know its temperature, which is around like 9,000, so like around right here. And then we can sketch which point it is. Alright. Okay. Okay, question 8. So this one is a thermal question. Small pieces of solid paraffin with a total mass of 30 grams at a temperature of 42 degrees Celsius are mixed with 150 grams of liquid paraffin at a temperature of 240 degrees Celsius. The mixture is stirred until an equilibrium temperature is reached. Following data for the paraffin are available. Calculate the theoretical equilibrium temperature of the mixture. Okay, so if we let the theoretical equilibrium be equilibrium is going to be T, then okay. Oh, this is an annoying question. So melting point of paraffin is 47 degrees. Okay, so since 42 degrees is really close to 47, and looking at the heat capacity not being a lot, I think it's safe to assume that the equilibrium temperature will be a liquid. So it's definitely going to be above 47 degrees. That's kind of my logic. I don't want to do this twice, obviously, so equilibrium, let's say, is T. So first of all, the temperature of the solid paraffin needs to reach T. Or let's just do the liquid first. Liquid's generally easier. So so ML CL delta T, which is 240 minus T. I can use Celsius here because I'm only dealing with differences in temperature. So that's the total energy put in. This equals, so the temperature of the mass of the solid paraffin, MSCS. So first of all, it needs to reach the melting point, right? So that's reaching the melting point. Then it needs to reach the the heat needs to be converted to latent heat of fusion, so that's going to be MSL. Latent heat of fusion is LF. And plus, it needs to reach the equilibrium temperature, so that is MSCL T minus 47. So yeah, there we go. You can solve this equation. You know ML, you know CL, you know MSCS, MSF, LF, MSCL. So you know everything. You can solve for this equation. Okay. When the experiment was carried out, the equilibrium temperature of the mixture was found to be different. Suggest the reason. Obviously some heat escaped. The mixture was held in a large metal container during the mixing. Explain one change to the procedure that will reduce the difference and reduce this. So obviously what they can do is so obviously a metal container would probably let a lot of heat through, because metal is a good conductor. They can do it either in maybe in a vacuum, so that there won't be any conduction or convection from the heat lost. Question 9 is capacitors, so we won't do that. And okay, so question 10. Right, so we can do question 10 for sure. Wow, question 10 is long. Okay. Object hangs in equilibrium from a spring of elastic constant K. The object is displaced through a vertical height h equals a and released at time t equals 0 so that it oscillates with a simple harmonic motion of period t. The graph shows the variation of h with t. State the equation of motion for this oscillation. So obviously this is simple harmonic motion with period t. So the equation for the simple harmonic motion, so it's starting at the top, so we will use cosine. It wants position versus t. So h, right, so h would equal amplitude cosine wt. And there's no phase difference because we're starting right here. So we can find w using 2 pi over t. So they gave us, did they give us the period? Oh, so it just wants to represent that using that. So therefore it's a cosine 2 pi over t. Sketch on the axis variation with t of the velocity v of the object. Label the peak values on the v-axis with an appropriate expression in terms of a and t. So velocity, okay. So this was the xt diagram. So this was xt. Then the VT diagram. The VT diagram, so obviously the speed is minimum here. It goes into negative maximum here. Once again goes to 0 here. Positive maximum here. Goes to 0 here. So I'll draw this better. So I'll draw the critical points down like that. So obviously we start at 0, or we start at negative, we get to negative maximum, and up, positive maximum, down, negative maximum, then up again. Yep, so that's VT, and so T would obviously be right here. Next one is part C. Okay, C waves are produced by wind and carry energy that can be transferred into electrical energy. A C wave can be modeled as a square wave of wavelength lambda, amplitude A, and width W. Show that the gravitational potential energy of the C wave shown in the diagram can be modeled as EP equals 1/4 rho G W lambda A squared, where rho is the density of the seawater. Okay, so taking a look at this equation, first of all, we want to dissect it. So this is obviously, they've scrunched a bunch of variables together. So now we see, we see this entire thing. So we want to take this apart. We know that potential energy is mgh. And we do in fact have G in here. I will write the final result here so that we have an idea of what we want to end up with. mgw lambda a squared. So we have the G. The G matches up. G, we're good. M and H. So what is H? H is the height of the wave. Now, half of the time the wave is going to be at the bottom, right? Half the time it's going to be at the top. So we're not really sure how we can describe H yet. So let's take a look at M. So the way M is calculated, M is equal to rho times volume, right? And there we go. There we have the density. The next thing we want is how can we represent the volume? Now the volume, we can represent this big block here. Let's see. So if we dissect this apart, the volume must have three components. And that's going to be W, lambda over 2, and A. So if we look at the dimensions here, W lambda over 2 times A, that's perfectly 3 of the points here. So if we can say volume is equal to this thing, then we essentially, we're almost there, right? So we can write this as rho W lambda over 2 times A. And how far are we now? So if we cancel this stuff out, lambda, lambda, rho and rho, we got that. A and A, we're really just left with an A over 2 factor. Where does this come from? Well, let's go back to H, because that's the only thing we're missing. We represented M. So M is just rho W lambda over 2 times A. G and G we've represented. Last thing is H. And we're missing A over 2. So let's think about this. Why might H be A over 2? Well, if the total height of the wave is A, then half the time it's going to be at the top, half the time it's at the bottom. Therefore, the average height is going to be A over 2. So therefore, H is A over 2. And then we can combine them all together to get rho W lambda 2 times A times G times A over 2, which is 1/4 rho G W lambda A squared. So this question was pretty good because it shows how I would dissect a problem and think about it logically. Right. Part 2. Right, so that was part 1. So when you approach a problem like this, don't be scared to, start out with formulas that you already have and look for clues in the solution as to why, and then explain kind of your thinking, especially for questions where they give you the final answer and they want you to try to show that is true. So part 2. The wave is moving at a speed v. The maximum power available from the sea waves is P. Okay, explain why the maximum power per unit length of the wavefront, P over W, available from the sea wave is half rho GVA squared. So once again, we want to think about this and how we can dissect our final answer, especially when they've given us, right? So if we take a look at P, how different is it from our thing here? P, we know that it's energy over time, right? So if we were to write P using energy over time, we would get 1/4 rho g w lambda a squared times 1/t. And if we divide this by w, if we cancel out the w, we're left with 1/2 rho g va squared. Rho g, and that's the speed, va squared. And look at this. Since lambda is this way, lambda over 2, so we can write this as 1/2 rho g, or we can write P over W as 1/2 rho g lambda a squared, or lambda over 2a squared times 1/t. And if we look at what lambda over t, well, lambda is the horizontal distance and t is time. And the waves is traveling horizontally. So what's distance over time? Well, that's just the speed. So therefore, this is just half rho g lambda over 2 times 1/t. That's just speed, a squared. And there we have it. So once again, looking at the final answer, we're able to dissect kind of how we would approach this and finally reach the final answer. Okay. Thermal energy is also used in the production of electrical energy. The thermal energy is usually transferred from the chemical energy of a fuel or from the nuclear energy of a fissionable element. Okay, a fuel is used to transfer thermal energy to water to produce at a pressure of 20 megapascals and a temperature of 550 degrees Celsius. The steam turns the blades of a turbine generator system and finally condenses at atmospheric pressure and a temperature of 30 degrees. Explain, with reference to the second law of thermodynamics, why a steam turbine operating between these temperatures must be less than about 60% efficient. Okay, so as we know, you want reference the second law of thermodynamics. Okay, so in this case, obviously, this is going to be an irreversible process because we're not doing ideal work. So that means entropy is going to be steadily increasing. And since entropy is steadily increasing, the efficiency is always going to be worse than the Carnot cycle, which we know is the most efficient engine operating at 2 temperatures. So therefore, by second law of thermodynamics, entropy is going to be greater than 0, and therefore efficiency is going to be less than the efficiency of Carnot. And we can calculate the efficiency of Carnot using 1 minus Tc over Th. And in this case, Tc is going to be 303, and Th is going to be 550 plus 273, so that's 823. So therefore, the efficiency has to be less than about 63%. Therefore, the efficiency is less than 63%, just as how we've proven. Alright, and the rest of the problem talks about nuclear decay. Which I will just skip. And yeah, that's it for this paper too. So that wasn't too bad. Pretty much speed ran in an hour. Yeah. Overall, I think if you understand the concepts pretty well, the physics final shouldn't be too bad for you guys. So yeah. If there's no more questions, I will just end the stream here. Thanks for coming, everyone. And next stream will be on Friday. I'll go over some HL Math past test. Alright. I will send this link. Yep, I will send this link in the chat, as well as this, so you guys can take a look at the answers as well. They have the mark schemes on here as well, so you guys can see. You guys can check the answers here. Oh, right, one last thing I want to talk about is the special relativity problem. I thought about it a bit more and I realized you can't actually use a space-time diagram to do this. So yeah, you can't use space-time diagram, because what it's asking for is determining which light pulse happened first in his frame, right? And if you use, the problem with space-time is that it's kind of hard to draw, right? Like, you're not gonna draw an accurate 0.8 C space-time diagram. So yeah. Yeah. That's it for the stream. Thanks for coming on. But yeah, any more questions? No more, I will end the stream here. Alright, no more questions. I'll sign off here. Of course, all the videos are going to be saved on the channel, so you can check these out whenever you want. So yeah, that's it. See you guys.